Today we will talk about glycolysis.
Let's start with
Phase 1. First of all, glucose will be converted into glucose 6-phosphate by the enzyme hexokinase. So from the name kinase, which means addition of phosphatic group, and hexo refers to the number 6, the phosphatic group will be added on carbon number 6 of a glucose molecule, where here from the name of the enzyme you can predict the upcoming product. Also at this stage we consume the first ATP molecule. Now glucose 6-phosphate is obtained. Another enzyme named phosphoglucoisomerase, so from the name isomerase, will convert the glucose 6-phosphate into its isomer fructose 6-phosphate, where these two compounds are just isomers but different in structure. Keep in mind that this conversion is really important because fructose 6-phosphate will be able to produce a specific product that glucose 6-phosphate structure cannot. Amazing! Now fructose 6-phosphate is obtained. An enzyme named phosphofructokinase PFK1, one of the most important enzymes that you should never forget, will add a phosphate group on carbon number 1, yielding a molecule named fructose 1,6-bis phosphate. So bis means 2 phosphate group. 1 phosphate group on carbon number 1 added by the kinase PFK1, and a phosphate group on carbon number 6 previously added. Also at this stage we consumed one energy molecule, ATP molecule. Don't forget that this stage is a reversible reaction, which means if we want to reverse fructose 1,6-bis phosphate again into fructose 6-phosphate, this conversion couldn't be mediated or catalyzed by the same enzyme PFK1, where here we need another enzyme. Why I mentioned that? Because if we want to reverse fructose 6-phosphate again into its isomer glucose 6-phosphate, this conversion could be catalyzed by phosphoglucoisomerase, the same enzyme. However, the conversion of fructose 6-phosphate into fructose 1,6-bis phosphate need a phosphate group, where we add a phosphate group on fructose 6-phosphate, forming the fructose 1,6-bis phosphate, a phosphate group on carbon number 6, and a phosphate group on carbon number 1, where this kind of addition needs a kinase. But because we are converting the fructose 1,6-bis phosphate into a fructose 6-phosphate, which means we will lose the phosphate group present on carbon number 1. In this case, we don't need a kinase, we need a phosphatase, an enzyme that removes a phosphate group. For that reason, this step specifically isn't mediated by the same enzyme. So for that reason, we mentioned that fructose 6-phosphate and fructose 1,6-bis phosphate is a kind of irreversible reaction. Then, this molecule will undergo the splitting state through adolase, producing glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. But good to know that glyceraldehyde 3-phosphate will be able to produce the products of phase 2. However, dihydroxyacetone phosphate, its isomer cannot. For that reason, dihydroxyacetone phosphate will be converted into its isomer glyceraldehyde 3-phosphate by the enzyme isomerase, thus yielding 2 glyceraldehyde 3-phosphate molecules instead of 1. Hence, the net product of phase 1 reactions is a glucose molecule, 2 ATP molecules, and 2 NADH molecule. After explaining the phase 1 reactions, now we will start with phase 2. First of all, glyceraldehyde 3-phosphate will be converted into 1,3-biphosphate glycerate by the enzyme glyceraldehyde 3-phosphate dehydrogenase. So from the name dehydrogenase, directly conclude it is a redox reaction, which means NAD+ will be reduced into NADH. This redox reaction is really important because the production of NADH will be essentially needed by one of the most prominent pathways used by the body for ATP production, the ATC cycle, electron transport chain cycle. Also here the PO4 represents the source of phosphate group from cytoplasm. Amazing! Now 1,3-biphosphate glycerate is produced. Another enzyme named phosphoglycerate kinase will convert the 1,3-biphosphate glycerate into 3-phosphoglycerate. Maybe you will be wondering how a kinase that add a phosphate group will remove a phosphate group from the yielded product. Okay, let's clear up the confusion. At this stage, the kinase addition of phosphate group or phosphorylation will be at the level of the substrate, which means the kinase source of phosphate will be from the 1,3-biphosphate glycerate, the phosphate group present on carbon number 1, and this phosphate group will be added on an ADP molecule for the aim of producing ATP energy molecule. For that reason, the yielded product loses one phosphate group. I hope I make it clear for you. Then this 3-phosphoglycerate will be converted by phosphoglycerate mutase into 2-phosphoglycerate. So mutase, which means mutate the position of phosphate group from carbon number 3 into carbon number 2. This mutation of phosphate position is needed because 2-phosphoglycerate will help in the synthesis of phosphoenol pyruvate. After producing the 2-phosphoglycerate, an enzyme named enolase will convert it into phosphoenol pyruvate. Phosphoenol pyruvate is a compound high in energy, so we will use from it a phosphate group and add it on an ATP molecule, yielding another energy molecule. Also here, the enzyme pyruvate kinase will be responsible for this addition and the conversion of phosphoenol pyruvate into pyruvate. So, why we multiply the glycolysis phase 2 products by 2? Okay, don't forget that at the end of phase 1, we converted dihydroxyacetone phosphate into glyceraldehyde triphosphate, which means yielding 2 glyceraldehyde triphosphate molecules instead of 1. And the steps showed here in phase 2 represent the conversion of 1 glyceraldehyde triphosphate into pyruvate. But instead of repeating the steps twice, immediately we will multiply the products of phase 2 by 2. Thus, the net product of phase 2 will be 2 pyruvate molecules, 2 ATP and 2 NADH. Maybe you'll ask yourself like how 2 ATP and per 1 glyceraldehyde triphosphate will produce 2 ATP, which means that from 2 glyceraldehyde triphosphate will produce 4 ATPs. That's true, but because we consumed 2 ATP in phase 1, from the 4 ATP produced in phase 2 will subtract the 2 ATP consumed in phase 1, hence which will be equal to 2 ATP remaining as a net at the end of glycolysis. Finally, we will sum up with the following slide, where in glycolysis from 1 glucose molecule we produce 2 pyruvate molecules, and the energy produced, which is ATP and NADH, ATP directly used by cells, NADH, a compound carrying electrons, will enter the ETC cycle and produce ATP. Here also we are summing up the phases of glycolysis, where first phase represents the conversion of a glucose into glyceraldehyde triphosphate by the use of energy, which means it is the phase of energy investment, and phase 2 is the conversion of glyceraldehyde triphosphate into pyruvate by capturing energy, where from the conversion of these two compounds, energy was produced, thus naming it phase of energy capture. By this, we will end the topic. Hope I make it clear for you. Don't forget to subscribe, and I will leave links in the description for other YouTube videos. Thanks a lot.